set of solutions is for this problem or set of problems for resistance, where first we're calculating the resistance of this composite system where the resistors in series, then calculating when it's in parallel, and then finally calculating the resistance of this spherical resistive shell. So for the first problem, we had this setup right here, where we had these resistors that are in series with one another. So we have some current that flows from left to right. So that, let me get the dimensions on this. This is A, B, row 0, row 1, W, and L. Okay, so some radius A, some radius of B. This is some W. This is some L. And then this is some row 0, and then this is going to be some row 1. So we want to find what the resistance of this entire system is. And so the way that we're going to go about that is, first we can write down the microscopic form of Ohm's law. E vector is going to be equal to rho J. Then the relationship between the current and the current density vector. So the current is going to be the flux of the current density. Then we can combine 1 and 2. Then we can find delta V by saying this is equal to the negative integral E dot dl from some R1 to some R2. And then the last thing that we can do is we can say from the macroscopic form of Ohm's law, delta V, the magnitude of delta V is going to be equal to I times R. And so when we do this calculation in line 4, we can compare it to what we have in line 5, and everything that is not a current is what the resistance is. So looking at this setup that we have here, we actually have 2 different current densities. We can call this some current density 1 and some current density 2. The current is the same in this resistor and this resistor. And so because the areas are different, that means the current densities are different. So from that, what we can do is we can say that J1 is going to be equal to I divided by the cross-sectional area that we have there. So that's going to be pi A squared. J2 is going to be equal to the current per cross-sectional area in the second region. Then we can calculate what the electric fields are. So E vector 1 is going to be equal to rho 0 times J1 vector. And then E2 is going to be equal to rho 1 times J2 vector, given this rho 0 and this rho 1 that I have here. And then to find the magnitude of delta V, this says that the magnitude of delta V, or just delta V, is going to be equal to the integral from 0 to L plus W, because when we're looking at this, we're defining the origin this way. So this is going to be x is equal to 0. And then we're going up to a point where this is going to be W plus L. And so that's the entire integral that we have here. But because we have a different electric field in each region, we have an electric field E1 in here, we have an electric field E2 here. That says then that this is going to be equal to negative integral from 0 to L E1 dot dl plus, we can factor out our negative sign, plus an integral from L to L plus W of E2 dot dl. And so we can plug these in and evaluate them. And so that says that this is going to be equal to the negative integral from 0 to L of, this is going to be rho I divided by pi A squared times dx plus the integral L to L plus W rho, this is a rho 0, this is a rho 1, I divided by pi B squared times dx. And evaluating these integrals, we end up seeing that the magnitude of delta V, so the magnitude of delta V is going to be equal to rho 0 I divided by pi A squared L plus rho 1 I divided by pi B squared times, this is going to be L plus W minus L, so this is going to be W. So then if we look at this, we could factor out the current I, and then we're left with rho 0 L divided by pi A squared plus rho 1 divided by pi B squared times W. This is the resistance R1. This is the resistance R2. And so this composite thing that we have here, we're saying that R1 plus R2 is equal to REQ. And so that's verifying that we can add these things in series. Okay. Again, I'm going through this quickly. It's important that you're going through all these steps yourself. I would actually suggest not, if you get to that point and you're watching the solution, it's probably, too late. But I would say make sure that you're doing this on your own first, because I can't solve the exam questions for you. Okay. So problem two. Problem two is kind of interesting because instead of looking at this in series, we're looking at it in parallel. And this was kind of a tough problem, but I wanted you to think about this and the way that you're constructing this and what's the same for this situation versus what's the same for this situation. What's the same for this situation is the current. The current is the same in both of these resistors. For this problem, the difference in electric potential. So if I talk about what the difference in electric potential is across this, that's the same for whether I'm in the inner region or the outer region. So this is going to be some radius of A. This is some radius of B. I think, let's see, what was the length that I gave this? This is a length of L. We have rho 0. So this is length of L. This is rho 0. This is rho as a function of X is going to be equal to rho 0 X squared divided by L squared. Okay, so for this one, what we can do in order to verify that this relationship holds for the composite resistance is to think about this in terms of a circuit diagram in conjunction to thinking about it in terms of the physical resistor that we have here. So if we call this one an R1, call this an R2. This is an R1. This is an R2. Okay. Then what we can do is we can calculate each of these independently. And so when we're doing this calculation, we could say that R is going to be equal to the integral of rho dl divided by A, where these are all functions of R in principle. And so if I wanted to do this like this, going from the beginning of the resistor to the end of the resistor in terms of the distance. So this is going from 0 to L. See if you can figure out where I got this equation from. I'm not going to give you this equation, but it comes from what I did here more generally. That's an important thing to work out yourself. You shouldn't believe me when I say that this equation is true. It happens to be. Most of the time, you're gonna have to figure out when it's not. So I'm going to use this here. And then this is going to say that for this R1 is going to be equal to rho 0 X squared divided by L squared divided by the cross-sectional area, which is going to be pi A squared, integrated from 0 to L dx. And so this is going to be equal to, this is going to be rho 0 L cubed divided by L squared divided by 3 pi A squared. We can cancel this right here. And so then R1 is going to be equal to rho 0 L divided by 3 pi A squared. We can do the same thing for R2. R2 is going to be equal to the integral from 0 to L of rho 0 dx divided by pi B squared minus A squared. And so this is going to be equal to rho 0 L divided by pi B squared minus A squared. Okay. So then the important thing here is to think about the fact that the current that goes in here, that I is the same as the sum of these two I's. So this is the junction rule. So I is going to be equal to I1 plus I2. But simultaneously, we also can say that V is equal to I REQ, which is equal to I1 R1, which is equal to I2 R2. And so this says that I is going to be equal to V divided by REQ. I1 is going to be equal to V divided by R1. I2 is going to be equal to V divided by R2. And so we can take all three of these things and plug that into this equation right here. And so we have V divided by REQ is equal to V divided by R1 plus V divided by R2. And then these are going to cancel. And so then what we're left with is that 1 over REQ is going to be equal to 1 over R1 plus 1 over R2. Okay. Last problem we have is this spherical shell where I have this some inner radius of A, some outer radius of B, and we make the current flow from the inner surface to the outer surface, where this is some resistivity of rho 0. So what we want to do, again, think about the flux of the current density vector. Sorry, this isn't over a closed surface. It's just over some surface where that surface happens to be a closed surface. So this is J dot dA. So what is the surface that we're adding this up over? Because it's spherical, this is going to be the surface area of a sphere. So this is going to be I is going to be equal to J times 4 pi r squared. So J is going to be equal to I divided by 4 pi r squared. This allows us to write the microscopic form of Ohm's law here by saying that E is equal to rho 0 times J, which in this case is going to be I divided by 4 pi r squared r hat. And then to find the magnitude of delta V, this is going to be equal to the negative integral from where we're beginning, which is going to be A, to where we end, which is B, of E dot dr. So this is going to be rho 0 I divided by 4 pi r squared dr. And so this is going to be equal to rho 0 times I divided by 4 pi times 1 over A minus 1 over B. Make this B, make this B. This is A, this is A as a magnitude. And then that goes away there. So then what we do is we say that this delta V is going to be equal to rho 0 I divided by 4 pi times B minus A divided by AB. So that's V is equal to this. We can factor out our I. So if we factor out our I, then this right here is what the resistance is. Okay, so that's it for the third problem. Like I said, I went really, really quickly through this just because I wanted to get you the solutions quickly. But the process that I went through is exactly the same process that I described. And there's a lot of pieces that I'm kind of connecting and I'm doing in my head because I've done this a lot. But it's important for you to actually write all of those things out because it's not likely that you'll be able to reproduce exactly what I'm doing unless you're practicing. For what I have written here, it is very logically consistent and it flows, but that's because I'm checking all these things in my head as I'm going because I've practiced this a lot. Okay, so that's going to be it for this video. The next one is going to be a video for the circuit analysis, the second circuit analysis. Okay, take it easy.